Hi. Over the next few minutes, we are going to discuss this topic called direction fields. They're also sometimes referred to as slope fields. Okay, and so the idea here, fields, is because we're going to have a sense of direction. So we want to think of the slopes. So you could have a positive slope. This is a sketch of a line with a positive slope. This here would be sketching a line that has slope equals 0, it's flat, horizontal. And then you can have a line that has slope that is negative, right? So this is positive slope, 0. Okay, so bigger than 0, equal to 0, less than 0 in terms of slope. M is a common a common notation for slope, so you can have positive, equal to 0, or negative. Okay, so that's the idea with this sense of direction that is going to define some sketch, and we're gonna use information we're familiar with, specifically information that we can derive from a differential equation. So we want to think of the right hand side of the differential equation as a function of two variables. So again, here we're assuming we're writing dy dx. That's the same as writing, writing y prime is the same as writing in Leibniz notation dy dx. And so we want to think that this here on the right hand side is an expression that involves both x and y, right? So this would be an expression of x and y, but we are always making the assumption when we write this is that y is a function of x being the independent variable, and y is an expression of x, but we can have a right hand side that involves both of them. What would be good examples? Well, how about something that looks like 2x times y, or let's visit some more type of examples. So but the idea also here is that we want to take information. After all, we are working on the two-dimensional plane, so we're going to think of these coordinates really as if they were coordinates in the sense of x, comma, y, but where y is a function of x. So if we know x, we know y. And so now we want to think in terms of x0, y0, a pair in the two-dimensional plane, maybe x1, y1, and maybe x2, y2, and x3, y3. And what do we do with all these pairs? Well, we'd like to evaluate. Okay, we want to evaluate the right-hand side into each of one of those. So we evaluate f at x0, y0. We evaluate the right-hand side at x1, y1. And we want to connect that to the meaning of this, which is dy dx. And so when we're evaluating, we are obtaining information. Okay, so let me write here dy dx equals f of that, but what we're saying there is that at x equals x1 and y equals y1, we are obtaining information about the slope of the tangent, in some sense, slope of the tangent at this point, x1, y1. So here we have a concrete example, an expression on the right hand side that is y squared minus 2x plus 5. So what happens if we evaluate dy dx at x equals 1 and y equals 0? So that means that we are going to evaluate this expression. Okay, y is 0, x is 1, and this gives us minus 2 plus 5 equals 3. Now, this 3 is going to have the meaning of the value of a slope. We want to think of a slope of a tangent to a curve. Okay, that curve would be defined in the two-dimensional plane, and that slope here being positive, we want to think of this as we're going to draw an arrow that illustrates a line with a positive slope. So what happens if we now evaluate dy dx at, so we work the first one, what happens if we evaluate now this at x equals 2 and y equals 1. So we square, multiply by 2 and add 5, right? So y, in this case, y is 1, x is 2. Okay, so this gives us 1 minus 4 plus 5. Okay, and this value is minus 3 plus 5 is 2. So this is still giving us a value of a slope that is positive. So that takes care of the second one. And now we do another evaluation using x equals 3 and y equals 1. So when we evaluate 3, 1 in the right hand side, then we obtain a value of 0, and this would be representing the slope equals 0 of some tangent line. So with these evaluations, we obtain a positive value, positive slope, positive value, positive slope, 0, which is a flat line, the slope of a flat line, horizontal line. And so the idea is that we could continue this evaluation in many, many points in the two-dimensional plane. And so that set of points in the two-dimensional plane, if we were going to do this consistently, would look like this. And so this is the type of job that you could do by hand, but is actually a very good job for a computer, which is exactly how this figure was generated here. And the point that I'm trying to make is that we want to be able to interpret these lines here are somehow, well, if I put the arrow, it's probably too much right now, but each of these lines, okay, the position of each of these lines is representing values of the slope of a tangent line to a curve. I have not said to you what is the curve, but the point is that when you see this type of graphic, this is what we are going to call a slope field. Okay, and let's perhaps identify some of those points that we are working with. The last point was 3, 1, so it had x had a value of 3 and y had a value of 1. So if we follow this, that point 3, 1 is somewhere around here, right? And 3, 1. So what we found out was that 3, 1, here is 3 in the x-axis, horizontal axis, and that's the height is about 1. And so at that point, 3, 1, the value we obtained was 0, and so we would draw a line that's kind of like a flat line, okay? But if we identify some of the other points, the second point was 2, 1, so the x coordinate 2 is right here. So I just moved that this line here, and you can see that that is positioned on the x coordinate equals 2, and at the point 2, 1, the value we obtained was a positive value, and you can see how that's exactly around this point the values of slope are quite positive, right? So if we were going to draw the slope exactly at that point, then we would sketch something that looks with that type of inclination, with that type of angle or slope, right? And so that's the idea with these type of plots. And more importantly is that we could sketch the slopes relative to the right hand side of the differential equation, and then we can do even more. We could decide, you know what, I'm gonna choose a point on this plane. For example, well, maybe I should talk about this point here. This point here would be 0, approximately 0, 1, And that point in the two-dimensional plane with an x coordinate and a y coordinate could then serve as information that we use in the initial conditions. For example, I'm going to specify that I want an initial condition with x equals 0 and y equals 1. And then I'm going to take a look at if I start with such values on the initial condition, this curve appearing here in red is telling us information about the so-called trajectory. And this trajectory is the trajectory of the solution of the differential equation. So I could choose to start at a different value, say minus 2, x equals minus 2 and y equals 3, for example. And then that would give me another initial condition. So the convenience of using some of these tools, these computational tools, is that you could generate a lot of these solutions by basically only point and click, right? So this offers each of these curves is a so-called trajectory, which is associated with the differential equation. And now once you see the slopes and you see the curves, then those slopes can convey the message. Basically, by reading the slope field, you can have a sense of the so-called behavior of the solutions of the differential equation. So this here is the direction field, or the slope field for a different differential equation. It's a differential equation which the right-hand side, dy dx, equals sine, and the argument of the sine function, the trigonometric function, the argument is the difference between y and x. It's y minus x. Okay, so right now this is for initial conditions at 0, 0, we would see that that solution appears. And so this is a quite nice, because of the definition of the sine function, this gives curves that are quite smooth, right? And so the idea of the slopes in this field is to kind of paint a picture of what the trajectories would look like.